Let's play with this a little more and see if we can construct a second-order factor. This would be useful when your scale has subscales. Each subscale comprises multiple items, but then the subscales themselves are actually manifestations of a larger underlying construct, or perhaps multiple larger underlying constructs. For example, in our case here, self-kindness, common humanity, and isolation are all subscales of self-compassion, so perhaps there is an overarching construct of self-compassion made up of these three. Now, if we wanted to build a second-order factor, well, how would that go? What do you think we would have to do here? Could you try and modify the input file in the model section to make space for this other second-order factor? Right, so we would need another by statement. So let's call that self-compassion, and it would be self-compassion by, and now the items for this are the three first-order factors that we already had: self, hum, and iso. And that's it. It's very easy, isn't it? What about this? Should we keep this in or should we take it out? What do you think? Right, so we should take these out. The relationship between these new items, the first-order factors, is now depicted by the presence of this factor. In fact, if we wanted to keep any kinds of correlations in, so for example, just say the correlations, they would no longer refer to the correlation between the factors, but they would refer to the residual correlations. How do we know it's a residual correlation? Well, that is because these first-order factors are now actually part of this by statement. What this means is that their variance was now split into two components. The proportion of variance that is joint across all three of them, which is expressed by the existence of this factor, and the unique variance which is left over for each of these. And it is this unique variance that's left over which is now taken up by these correlations. Technically speaking, it's really us who decide that this is a residual variance, mainly because we believe this to be kind of like the main dish, and this is the leftover. But what the software does is it simply pulls the joint variance and partitions it from the other variance, and the joint variance is used in the factor, and the other variance is used in these correlations. So that's why we call them residual correlations. It's the same for everything that is a part of a model like this, so we could also have residual correlations between the direct, manifest, observed items as well. And we would write them in the same way by just using with statements. So let's take this out. And there you go. Now you have seen how you specify residual correlations, but also how to specify a second-order factor. It's very easy. Now I'll show you the results in a second, but I do have a question to you first. The question is, if you had to decide whether you should write this as a second-order structure or a first-order structure, what would you choose? Would you have chosen to do a second-order factor? Should we have chosen one or should we not have? Have a little think. Okay, so I would choose not to have a second-order factor. The reason I would choose not to have one is because we noticed in the previous output that there were no correlations between our factors. Like I said before, the whole purpose of a factor is to pull together the joint variance of its items, but we don't have any. So what this should mean in practice is that if we put this factor in, the loadings that we get should be not significant. So let's run this model and have a look. So we are now in the output file. And if you scroll down, you now get this warning. The latent variable covariance matrix is not positive definite. Then you scroll down further, and you see now that the model fit is no longer quite as good as it was before. So already things are not really panning out for us. So you scroll down a bit more, and you see exactly what I told you. The loadings are not significant. That's because these 3 first-order factors were not correlated to begin with. And also, with regard to that warning we just got, the reason for it is this. The variance for self-compassion is negative. So this is because it's so close to 0 that it kind of flipped over to the other side of the continuum. But this is something known as a Haywood case. It is an impossible coefficient. That's because we always expect to get some variation between responses, and the minimum of variation we can expect is 0. So it is practically impossible, in fact it is also theoretically impossible, to get a negative variation in responses. So this is why we had this warning here. In any case, you will sometimes have beautiful second-order factors, which you can then use further in your analysis. And this is how you do it. It's very simple. And also you can get structures with more subscales and more second-order factors, and you can even have third-order factors if you have such a complex factorial structure. Now let's have a quick look at the diagram. So this is what the diagram looks like. It's really beautiful, don't you think? Now let me take out the standard errors. And here we have the unstandardized results, and it looks wonderful. However, if you ask to see only the significant parts, you see that these two disappear. So perhaps it's not so beautiful after all. This one with a loading of 1 here did not disappear because this loading was fixed in order to provide the metric for this factor here. So this is it. We now know how to specify a second-order factor and have also learned a little bit about residual variances in the process. Well done!